Okay, so first we're going to get onto the lesser gas laws. So these are some of the smaller gas laws that will ultimately make up the ideal gas equation. So these laws were basically found by the scientists, the old scientists working away in the basements, and they just happened to find some relationships, and then they quantified them using a law. So this dude called Boyle, right? He came up with his Boyle's law, which is that the pressure of a fixed amount of gas is inversely proportional to its volume for a given temperature. So P times V equals some K. Does that make sense? We can kind of see how he came to that conclusion. Okay, so this is his experimental setup, right? So over here, I can see that the total volume is going to be 20 mil, and the total pressure is going to be 760 millimeters of mercury. So this is from the atmospheric pressure over here. Remember 1 atm? 1 atm equals 760 mmHg. But also there's 20 additional millimeters of pressure here. And that's going to exert the same amount of pressure as this 20 volume of 20 moles of gas over here. Okay, now I want you guys to calculate the pressure now. Pressure over here, P2. What does that equal? So Bill, can you calculate the pressure for me over here in the second instance? In this over here.
Okay. Is the triangle H equal to like the is that the mercury thing?
Yeah, that's the millimeters of mercury, yeah?
Okay.
The pressure was 780 in total. 780 in total.
Okay.
Because we're adding the 760 millimeters of mercury from our atmosphere and the 20 millimeters of mercury from our tube over here.
Okay.
So you would have known if you were,
Okay.
paying attention. But don't worry. So in pressure 2 over here, our pressure would be 760 millimeters of mercury because the atmospheric pressure is still here.
Yeah.
And then
Plus
what would our second
800.
thing? Plus 800. So that equals?
That equals to 1560.
So look, now our pressure is 1560 millimeters of mercury and our volume is only 10 mil. So you'll see that when I doubled my pressure, I halved my volume, which leads us to our conclusion. Yeah, inversely
It's inversely
proportional.
proportional?
Inversely proportional. PV equals K. That's amazing. Good job. You were a 18th, 17th century scientist. Not bad. Okay. So, I also kind of want to give you guys a bit of intuition behind these laws. So remember, pressure is the collision between the walls of the gas, walls of the container, and the molecules of gas, right? So if I reduce the space that the gas takes up, it will collide with the walls of the container more, and that results in a higher pressure. So I have a bit of a demonstration for you guys. If I have this volume over here, pretend this is my gas molecules in my little container. So right now they have to travel a really long way to get to hit the wall of the container, right? And count as pressure, right? But if I reduce the volume, now they have to travel much less, and therefore that increases the pressure. So because they travel less, they hit the walls of the container more, and that increases pressure. So less volume equals higher pressure. And finally, our implication. For the same temperature, K will be the same, and therefore P1 V1 equals K equals PV, P2 V2. Cool. And a really note here is that you must use the same units of pressure and volume on both sides of the equation. So this is like our dilution formula, remember? You must use the same. This must be in the same unit as this P2, and this V must be in the same unit as this V2 over here. So I use liters and kilopascals. I need to use kilopascals, and I will get out liters. Yep, just keep taking notes. So yeah, same units of pressure and volume must be used on both sides of the equation. Okay.